Stein Atle Haugerud, that he will talk about the chapter 7 design principles. Stein Atle, if you are ready, you can share your screen also.
Thank you, David. My name is Stein Atle Haugerud. I'm working with Dr. Teknola Olsen in Norway, Oslo. I'm a structural engineer specialized in marine and offshore structures. I will take you through the next section related to design principles, and the next 45 minutes we will share some general design consideration and also some specific recommendations for dealing with the challenges we face in designing SFTB concepts. So the design principles will be presented as we also have done it in the bulletin, following the natural steps of developing a crossing concept. That is starting with the overall crossing layout and considerations to determine the structural configuration, and then we will look on support systems and global stabilization and further touch on typical aspects of structural analysis and design of an SFTB. And finally, we will, as we are dealing with a novel concept, we will also address the importance of safety and how to enhance robustness of these concepts. So finding the most effective and favorable concept will normally require a screening of several crossing schemes and not only looking at one. The overall workflow for preparation of preliminary crossing layouts include briefly a selection of the crossing corridor and more in detail deciding the alignment, then work out the general dimensions and layout of the tube, and then next decide on the support system for stabilization of the tube in the both directions, and finally also decide on and work out the span arrangement. So alignment and length are not usually strictly defined parameters when you start to work out the alignment for an SFTB. And this means that various crossing trajectories will have to be explored to find the most effective one. And on the positive side, this means that the horizontal and vertical alignments are usually uncoupled and can be worked and tweaked separately. So if we start with the horizontal alignment, possible landfall locations and routing of the access or land tunnels will represent typical constraints for the alignment. As we can see in this example at the right shore, the landfall position follows as a shear consequence of the alignment of the access tunnel, where the rock tunnel had to be routed in parallel or in between the weakness zones in the rock. Furthermore, different support systems will call for different considerations as well. For an anchored SFTB, the bathymetry and seabed conditions and possible anchor locations will have to be considered early on when developing the plan alignment. This may have to be based on quite uncertain basis, since data from the field service, as we heard earlier today, are not always available in the early stage. But a lot of information can be obtained from just interpreting depth contour maps and sea charts and also looking on the surrounding terrain and typography. So for a pontoon stabilized tube bridge being independent of the seabed conditions, locations and width of the ship channel, if required, will affect the pontoon arrangement. And the width of a fairway will depend on the ship traffic, and for a main fairway typically be in the order of 250 to 400 meters for a one-way passage. So when laying out the alignment, the shortest route between the shore connections is naturally a natural first choice, but not always the best choice for an SFTB. As we will see later on, the horizontal geometry is an effective tool to tune the dynamic behavior of the bridge and also to provide horizontal stability, as we see here in the case of a horizontal arch. In the vertical plane, the SFTB offers great alignment flexibility and allows a shallow vertical profile with a little or even no gradient. In lakes with no boat traffic, a draft just below the influence of the water level fluctuations and maybe also the seasonal temperature variations would be sufficient. In waters with the ship traffic, the traffic profile has only to accommodate a safe sailing depth, and this is normally set by the navigation authorities. But pending such a decision or such input for main fairways, a minimum free clearance of 20 meters above the tube will usually be sufficient, and the sailing depth can also be less, let's say down to 14 and even 15, 14 meters in some cases. A deeper draft may also be utilized to reduce the hydrodynamic response in the tube. As we heard earlier, we recognize the diagram showing the penetration of the wave loads with the depth. As we can see, the wave energy decreases exponentially with the water depth, and also evident is that the effect is strongly dependent on the wave period. Ocean swells have longer wavelengths and can transfer more energy down into the deep than the shorter wind generated waves, which we find typically below 6 seconds. 5 to 6 seconds. So while it would be fairly impractical to avoid all loading from a long periodic swell wave by increasing the draft, a moderate lowering of the tube bridge will significantly reduce the excitation from wind seas. So, and as an example, increasing the water depth from 20 to 30 meters will reduce the action from wind seas by wind waves by about 75%. And for a concept which is struggling with resonance, that could be a lot. The vertical profile will in the end be a trade-off between a deeper and longer approach tunnel and also a more demanding marine operations versus lower hydrodynamic loading on the SFTB. After having laid out the alignment, the next step is to figure out the structure arrangement, and we will start with the tube structure. The tube bridge, for tube bridges, a large variety of cross-section demands can be accommodated. And the cross-sectional shape develops from the required traffic envelopes, escape corridors, and space required for ballast and drainage and ventilation systems. A stead space will be or imply extra ballast weight and more drag and increased hydrodynamic added mass. A compact packing of the different space requirements is important, and the best packing is normally obtained by a rectangular cross-section, which will also probably result in the most economical fabrication. But the rectangular shape is less favorable in terms of hydrodynamic behavior. Compared to a cylindrical shape, the box shape will attract significantly higher current forces and also increase the vertical component of the wave forces. And for a marine crossing exposed to high currents and swell waves, the hydrodynamic performance is much more important than optimizing the weight displacement ratio. This is a typical cross-section layout, which you have probably seen before. It has been favored in recent Norwegian studies, both in single and also in twin tube arrangements. And despite a fairly large area ratio between the tube inner profile and the traffic envelope of nearly 2.5, an effective utilization of the cross-sectional area is still obtained. The free headroom offers ample room for ventilation fans and traffic signals and signboards, and below the traffic deck we have ample space for 3 compartments with 2 of the other outer ones dedicated to solid and wet ballasting, and the central compartment serving as a service gallery where we can route piping and all the utility lines. The contingency on net buoyancy, as mentioned by Annette earlier today, occupies a large or considerable space in the cross section. As can be seen from the cross section here, the ballast compartment can typically take up to 10 to 15 and even more percent of the interior space of the tube, and is important to consider when you are starting drafting a cross section. So regarding material choice, the tube may be in concrete or steel. Each material has its own advantages and limitations. The common criteria for selecting tube material are usually material costs and durability and site conditions, and may also local construction practices and preferences. Among the studies we have listed in the bulletins, there is a clear trend towards concrete tubes, and the preference for concrete is due to various factors, of which cost and durability and maintenance perhaps are the most decisive ones. One of the biggest advantages of steel normally versus concrete is weight savings, but for a structure with excessive buoyancy, the favorable strength to weight ratio is not that useful. So a steel tube will also require nearly the same amount of concrete, about 80–90% as in a concrete tube, to achieve the same required net buoyancy. So given suitable site conditions and the direct fabrication costs for a concrete tube are likely to be significantly lower than for a steel tube. A steel tube may, however, under certain site constraints, still be a more economical option, and that would be in cases where there is no access to suitable dry docks, or where the towing draft is limited. As for an immersed tunnel, different cross-sectional variants or topologies can be envisaged also for a steel SFTB as well. The basic configuration categories are single shell, a double shell, and also, as we heard earlier, a sandwich tube structure. All these 3 variants have a cell grid buildup of longitudinal web plates and ring stiffeners supporting the skin plate or plates. Composite action will, with the infill concrete, can be utilized for all 3 of them, but we should say that composite action in the tube longitudinal direction should be carefully handled for an SFTB exposed to significant hydrodynamic loading, to avoid large uncertainties regarding dynamic behavior and response due to the cracking of the concrete. I said the main advantage of steel shell tubes lies in the fabrication and construction methods. A recent example of the efficient application of a steel tube is the Söderström tunnel, which we heard about earlier this morning. The single shell structure used for the tunnel is here acting as a waterproof membrane and serves also as a floating formwork. And the steel elements were fabricated in a shipyard and transported to the site on a barge and then lowered into the sea. And the interior concrete was cast while afloat near the crossing site, as you might can see in the top right photo. Now we go over to concrete. While different structural topologies are possible for a steel tube, the configuration of an all concrete tube is less diverse and typically consists of a concrete single shell which will constitute the pressure hull. Water tightness of the monolithic tube is ensured by a combination of strict design requirements and measures also during construction to control early edge cracking. Load-induced cracking is controlled through structural design and appropriate limits to cracking. And the tube will be subjected to both in-plane and out-of-plane action effects and is post-tension in the longitudinal and also in the hoop direction to prevent through the wall cracking. So a fairly high level of pre-stress is required, in particular in the longitudinal direction, to maintain a residual compression across the section under extreme loading events. We were talking about water tightness and membranes earlier today. The experience from the offshore concrete platforms and recent European immersed tunnels is that the external waterproofing membrane is not necessary, provided a proper concrete mix design, a good workmanship, and some actions to minimize early edge cracking, in particular controlling the hydration heat process. Longitudinal construction joints can be avoided using the full face casting technique, which has now become the state of practice for immersed tunnels. An all concrete tube does not have the same draft flexibility as a steel tube. Concrete tube will have the freeboard of only 1 to 2 meters when out of dock and require access to an offshore dock or a casting basin, as we saw Gordon was showing us. This may imply remote construction, but luckily sea transports are not very expensive, and besides also owing to the high longitudinal pre-stress, the concrete tube elements are well suited for offshore towing. A concrete tube will, like a steel tube, also have the need for passive fire protection to maintain structural integrity during the specified fire exposure. And in addition, polypropylene fibers can be added to in the cast of the inner face of the soffit or roof slab to inhibit explosive spalling in the event of a fire. And as to the durability strategy for an all concrete tube, again, in seawater would typically be the same as has proven effective for the North Sea concrete platforms. A high performance concrete combined with a sacrificial anode cathodic protection for the reinforcement and also embedded steel components. Some remarks also to the tube arrangement. Modern tunnel standards and also safety standards will require separate traffic boards, at least for major crossings. As we have seen, this can be obtained either in a single tube with 2 separate traffic compartments, as shown here in the top row, or in 2 individual tubes, as shown in the bottom. For the twin tube arrangement, the tube spacing is a key parameter that affects the horizontal flexural stability and stiffness, and also influences the bridge's sway characteristics and inline wave response. So for a crossing exposed to high wave and currents, the twin tube arrangement will be the natural choice. The full rectangular box section, especially the side-by-side configuration, will have significantly higher added hydrodynamic mass in the vertical modes, and will produce wave inertia actions, which are in the range of 2 up to even 5 times higher than the twin tube. Some comments to joints, and this is a common misunderstanding and confusion with the immersed tunnels. The SFTB is a multi-span structure that acts as a girder bridge, continuous girder bridge. It's made up of prefabricated tube elements, as we have seen, and monolithically connected to a continuous superstructure without any flexible joints. Only in special cases, like in high seismic zones, arrangement of dissipative joints may be required, and then only at the shore connections. So here we see examples of different jointing methods. We saw some earlier. One developed for floating position, and to the right, an alternative developed for fully submerged jointing, which is made of a steel connector with rubber gaskets, and which is also designed for a full robot welded connection. The landfall structures will provide end supports for the tube bridge and also secure a watertight connection with the approach tunnels or land tunnels. The structural configuration of the landfalls will largely depend on the seabed slope and the ground conditions, and type also of approaches. Since the landfall structures may have to transfer big forces from the bridge, ground conditions and location should be reflected early on in the development process. Steep slopes with hard rock conditions and little sediment overburden is considered to be ideal conditions for landfall locations. The method for connecting an SFTB to a hard rock tunnel can be based on the underwater tunnel piercing technique used for hydropower intake tunnels and gas pipe tie-ins. The underwater tunnel piercing method, which is shown in these sketches, is well proven and has been used in the construction of over 70 reservoir intakes in Norway, and even down to water depths of 150-160 meters. In soft ground conditions, the SFTB may be linked to a cut and cover tunnel. The transition element can, depending on the vertical alignment, be constructed either in situ within a dry excavation pit, or installed also wet by immersed tunnel technique in a trenched canal. In seismic regions, the interface between the tube and landfall structures represent a general challenge and may require shore connections with the dissipative capabilities. There are several examples of seismic thermal joints, not only from studies, but also from real-life projects. And I think the most prominent one is the triaxial seismic joint for the Transbay Tunnel in San Francisco, which was put to test and performed successfully during the 1989 earthquake. Other concepts to look on could be the Messina Strait crossing, and also some immersed hull projects in Turkey, for instance. Now we can look on the various methods for controlling vertical and horizontal stability of the SFTB. Compared to a bridge in air, a submerged floating tube bridge is practically weightless, and the tube is also very stiff, as the cross-section is often defined by space rather than resistance. Large span lengths can be obtained, and in sheltered waters, the maximum span length is typically governed by the water tightness, which can be easily be predicted. Recent example of a fixed single span tube bridge is the crossing of the narrow Digernes channel in Norway, as Ariana mentioned, having a span length of 500 meters and rectangular cross section with an over-under stacking of the traffic pores. When exposed to wave loading, the stabilization of the tube is different. A tube bridge represents a large structural mass, and together with almost about the same magnitude of added mass from the surrounding water, the structural damping is low, generally below 1% due to the heavy pre-stress. Moderate deflections also limit the hydrodynamic damping. So the SFTB concept is therefore sensitive to resonant behavior for wave periods within the range of the natural periods of the bridge. So tuning of the dynamic characteristics of the bridge to avoid resonant behavior is therefore an essential part of selecting the support configuration. We've seen this figure sometime earlier today, and SFTB carries a large part of the vertical action by buoyancy, as we now know. The difference between vertical actions and buoyancy will have to be carried to the supports and landfalls by beam action. And the supports can be designed either by as a pontoon floating at the surface, or tether anchored to the seabed, or even underwater columns. And each of these support concepts will have imply different buoyancy strategies for the tube. In a pontoon stabilized tube bridge, the pontoons control the vertical position and also motions of the tube. Vertically, the tube bridge acts as a continuous beam on discrete elastic supports, defined where the spring characteristics is defined by the water plane stiffness of the pontoons, and any variations in weight, buoyancy, and live loads will be counteracted by vertical displacement of the pontoons. So the pontoon concept has the benefit of being independent of the seabed and water depth, and any uncertainties related to seabed conditions and geohazards can be avoided. On the other hand, a pontoon bridge restricts the free passage of ships and must cope with a potential risk of ship impact. The span arrangement can normally be decided based on the static loading alone. The hydrodynamic response in the tube is little influenced by span length, as the heave excitation tends to be governed by the global heave modes rather than higher order modes within each of the spans. Some remarks to the response characteristics of pontoons. The heave response in a pontoon stabilized bridge is significantly higher than in a tether supported bridge. The pontoons contribute to the vertical damping, but will also attract significant loads from the surface waves. A pontoon system will have a vertical stiffness of only about 10% compared to a tether system for the same crossing, and is likely to be in resonance in heave for both swell and wind-induced waves. And the hydrodynamic excitation forces on pontoons in heave tend to be in the same order of magnitude as they are on the tube. So the sum is about the double as you would expect for a tether concept. In principle, a pontoon supported tube may have both positive or negative buoyancy. It's a free choice. A common strategy is, however, to trim the tube so that the bending moments or bending response on the permanent loading and live loading are of practically the same magnitude, but then with opposite signs. As to the sizing of the pontoons, the waterplane area is largely governed by the vertical stiffness required to control the deflections under traffic loading. And the shape can moreover be utilized to control the wave roll behavior and also potential adverse torsion from ship impact. The draft should be deep enough to avoid wave slamming on the underside of the pontoon, and also the freeboard should be generous enough to prevent water on deck or wave overtopping. As the tube, the pontoons can be of steel or concrete. Steel pontoon design is a standard ship type construction, which is suited for fabrication in shipyards, in ship docks, or even slipways. In marine environment, the splash zone corrosion is, however, a major concern or problem, since the cathodic protection is not reliable here, and the maintenance is costly. So there are attempts to solve this, and in recent Norwegian fjord crossing projects, the application of super duplex stainless steel skin plates within the splash zone belt is currently being investigated to aim to obtain a maintenance-free pontoon structure. Concrete, on the other hand, offers distinct advantages over steel in terms of construction cost and robustness, and also durability, but it is likely to produce increased heave response as a consequence of a much higher pontoon mass. Concrete pontoons can be built in ship docks and have a typical configuration as shown here, with an outer post-tension hull stiffened by regularly spaced bulkheads and diaphragm walls. For the connection with the tube, different structural types have been considered, like the cylindrical steel shaft and steel tubular trusses, as shown in here, and what we also saw earlier today. The capability of resisting a severe impact from ship implies special challenges for the design of the rigid pontoon tube connection. And to prevent overloading of the tube structure, a fail-safe mechanism to the connection may be a mitigation measure to maintain the structural integrity. A structural fuse concept has been investigated through several studies in Norway the last years, and from the investigation of different weak link concepts, a steel truss system, as you see here, made up of vertical columns carrying axial action and cross-bracing resisting horizontal loading, has been proven to be the best solution so far. Now over to tethers. A tether stabilized SFTB is positively buoyant and is tied down to the seabed by tension in the tethers. The buoyancy surplus can be distributed along the length of the tube, or probably more economically concentrated near the tether supports. The excess buoyancy is utilized as pre-tension for the tethers to prevent slack in operation. And vertically, a tether-supported tube bridge will act as a continuous beam on rigid supports, and since it's entirely submerged, a tether stabilized tube bridge is not influenced by tides or water level variations. And besides of being fully invisible, it's also out of the reach of ships. Drawback is though that its foundations are dependent on seabed soils and rock and slope parameters, which are at some stage will require extensive seabed mapping and marine geotechnical service. So despite in Norway, the tether alternative has proven to be the preferred solutions even for water depth down to 500 meters and also for fairly demanding seabed conditions. The tether supported bridge system involves a minimum of structural and hydrodynamic damping, and to avoid the vertical resonant behavior, the eigenperiods of the bridge needs to be tuned down below the period range of wind generated C, which is normally about 5 or 4 seconds. So given the mass and stiffness of the tube, the key parameters for tuning the dynamic performance are essentially mooring spacing and then the number of tethers in each tether group. The mooring spacing should also be limited to avoid higher order modes of vibration within each span. And this shows the typical solution for a tether assembly, and also some solutions for the foundations, which we heard Gordon tell you about. So I can only say that, or add to the tether, the tether assembly are normally developed for the tension leg platforms for large horizontal displacements, and for a submerged floating tube bridge we will have far less horizontal offset, and that means that we can simplify both the top connector and bottom connector to get a more economical system. Now to the last variant, a tube supported on fixed support is less common, but can be a highly efficient support concept for moderate water depth. Support on columns, which has, for example, been proposed for the Lake Lugano and also recently Lake Geneva crossing, is applicable to water depths down to 100 or even 150 meters. The columns will restrain horizontal and vertical displacement in the tube, and with reasonable choice of span length, all natural eigenperiods of the SFTB can be tuned fully below the wave energy domain. To facilitate the construction in a lake without access to marine equipment or industry, the column supports are typically made up of hollow tubular concrete shafts designed to be constructed afloat and installed on its own keel. And here again, proven foundation techniques applicable for different soil conditions can be adopted from the offshore industry. So far, we have talked about systems for vertical support of a tube bridge. There are, of course, also horizontal actions from wave and currents and wind, as we know now, that need to be transferred through the structural system and into the foundations. Pontoons are and vertical tethers provide no contribution to the horizontal stiffness, and therefore the structure needs stabilization in sway to control the horizontal offset. Commonly, this is obtained by arch action, as we have seen, through a curved horizontal alignment. The arch shape, which is often referred to as end anchorage, enables greater resistance against horizontal actions. It provides flexibility for thermal expansion and eliminates the first mode with 1/2 wave between the end supports. And the end anchorage concept has been proven to be feasible up to 2,000 meters and for a single tube, and even 5,000 meters for a twin tube configuration. For a tether supported tube bridge, additional horizontal stiffness may be obtained by inclined tethers, as seen in several of the crossing studies. Among the various mooring configuration proposed, a system of 4 inclined tethers, as shown in the top figure, has been proven especially effective, as it also provides significant torsional restraint. Compared to the horizontal eigenperiods of the tube, the wave action is a fairly narrow banded process, and this fact allows us to tune the eigenperiods with sufficient gap margin not to coincide with the peak wave energy periods. So changes of the cross-section will typically move all eigenperiods, whereas geometric stiffness might be used to move discrete eigenperiods of specific modes only. So for a twin tube bridge, the main tuning parameters would be to the tube spacing and the shape of the horizontal alignment, as seen in the mode diagram to the right. And here we could think of only in addition to the arc, we also have the S and the double S configuration, which could be used to push off some complex acting eigenperiods. Obviously, it will not be possible to totally avoid resonant behavior, but the excitation can be greatly reduced this way and through the tweaking of eigenperiods. Now, let's turn to aspects of structural analysis and design. For the in-place condition, the structural analysis of the SFTB can be divided into a quasi-static response analysis for actions with no or small inertia effects, and a dynamic response analysis. And the results of the analysis will then be combined to extreme values and then used as an input for the structural design of the structure and structural components. A typical setup for the analysis and design is shown here with separate quasi-static and hydrodynamic response predictions using 2 different commercial softwares. And in order to handle large amount of design variations, pre and post processor routines are used to generate the global models and also loads from a parametric concept model, and also to extract hydrodynamic design loads from the time domain analysis and to produce final design load combinations for the structural design. The analysis can be carried out with finite element program using beam and truss and spring elements. Local actions like water pressure difference and hoop pre-stressing and also explosion can be considered in the detailed structural design of the tube shell. So for a sheltered crossing, the hydrodynamic response can normally be predicted by a frequency domain approach. For a crossing subjected to more severe environmental loads, simulation of a realistic correlation of wave action in both time and space is essential. A time domain analysis would then be used, and the hydrodynamic response predictions in the time domain is a fairly extensive topic, almost worth a webinar on its own. So I will refer you to the documentation of recent Norwegian studies, which are public and also available online. And we have also included some references in the bulletin. To the structural design of the tube, water tightness, as we now know, is crucial for the integrity of the SFTB. For an all concrete tube, the limit state of tightness will govern the structural design. Water tightness is commonly ensured by maintaining membrane compression, as we have heard, for the most adverse combination of unfactored characteristic loads. Water tightness criteria need also be established for the ultimate limit state and accidental events, and to ensure structural resistance and also integrity. A common criterion is to avoid any plastic yielding of the pre-stress and reinforcement. Specifying leakage criteria during a storm event can also be another option. The tube is acting as a shell structure subjected to both in-plane and out-of-plane action. Firstly, this will require a consistent design method considering equilibrium and compatibility for all the force components which are producing membrane stresses. And secondly, a transformation of the beam forces into shell forces. One pragmatic way of doing this could be to apply the beam response to a local FE shell model by a master-slave connection as shown here, and then perform the design checks for a ring section and undisturbed from the boundary conditions. As to the mooring system, there are two main criteria for the tethers, both related to ultimate limit state. That is, one, to avoid slack during the lifetime, and two, no overstressing of the tethers. In this diagram showing the load effect of a single tether installed with a nominal pre-tension of 10 meganewton, these criteria can be seen as the horizontal line for zero tether force, and also the dashed line for the ultimate tension resistant at 21 meganewton. So from the red unfactored force range, we can see that the static range is considerable, and tolerances of the self-weight and buoyancy has a significant impact. And we also notice that the traffic loading is the governing load for checking the slack criterion. The slack criterion in green, for this check, the full correlation of all unfavorable load contributions are conservatively assumed. And then from the tether capacity check in the blue range, we can see that the structural tolerances and buoyancy again are the governing loads, whereas the contribution from the hydrodynamic loads are rather moderate. Ample capacity margin is here obtained with a yield strength of only 235 MPa, clearly showing that the tether cross-sectional area is governed by stiffness and not by strength. So for comparison, the yield strength in a tension leg platform would be typically 480 MPa. Briefly to the pontoons, as for the tube, water tightness is crucial also for the concrete pontoon. The same design criteria applies for the outer hull and will also require the application of orthogonal post-tensioning. The design of the wall and plates for pressure loads is fairly straightforward. The main challenge for the design of the pontoons will be the design for a ship impact, which may require several transit analysis for reflecting several impact scenarios. And the pontoon will also have to satisfy an accidental flooding of any two compartments. Finally, to some remarks to robustness, as the SFTB represent a novel concept without any previous service history. Safety and robustness is a highly important issue when developing new concepts. A minimum requirement is that the SFTB should have the same level of safety as any other bridge or tunnel crossing. So consequently, potential accidental events such as ship impact and explosion and fire and earthquake should be devoted considerable attention. The requirement for on maintaining global stability in case of one element failure is a mean to incorporate robustness in design, being also a normal requirement for offshore structures. And for the SFTB, this would imply the design for a loss of a tether and or loss of a pontoon. Another way to implement robustness is to incorporate extra trim contingency for instance to compensate for unintended slack in a tether or provide extra freeboard or ballast reserves for the pontoons. Another an effective mean to demonstrate robustness is to perform sensitivity studies on key concept parameters and governing design drivers, such as wave height and wave period, wave directions, and damping, and so on. A concept showing little sensitivity to variations to key concept parameters is as a robust concept that will have the ability to withstand an unexpected situation, both in upcoming design and also in operations. Yeah, I think that concludes my presentation.